Hello everyone. Today we discuss contest 3. Let me show the script. So results are okay. Again, the contest is kind of easier than the previous ones, but results are not actually that much better than the previous one. I'm not sure why. But again, so problem F probably. F is which one? Problem F is probably tricky if you never saw something like this before, but yes. Okay, so again, so first 5 problems. Maybe the reason why you feel the contest is easier than the previous one is because first 5 problems are kind of easy. So sometimes I have problem D and E are kind of tricky. This time not. So for all 5 first problems, have no surprises. Just solve them like you think they will solve, and you just get accepted. Okay, so some actually managed to get some wrong answers in these problems, but we will read your solutions and see how did you get it. Well, let's go. So first problem is very simple. So in the first problem, you just need to okay, so you have permutation, but it doesn't matter. You only care about numbers 1 and n in this permutation. So you care about position of two numbers, number 1 and number n. And you want them to be as far as possible. And you do it by making exactly one swap. So you can swap two elements, and you want to put elements 1 and n as far as possible. Now, if you think about it, in one swap, you only can move one of these numbers, yeah? If you move both of them, it means you swap them. It doesn't make much sense. They have the same distance, yeah? So you move one of them, and if you think about where do you move them either to the first position or to the last position. So if you want maximize distance, you either move it to the maximum to the left or to the right, yeah? So that's all. So you have basically you have 4 options. You can move number 1 to the left position or to the right position, or you can move number n to the leftmost position to the rightmost position. And you just calculate maximum of these 4 options. Okay, I'm doing it. Okay, so it's not Python. You're not allowed to make maximum forms. I believe there is way to make maximum of 4 elements in C++. Like make array of them and then call maximum of this array, something like this. But okay, I decided I would do it like this. So it's just maximum of these 4 options, and that's it. So that's it. So that's problem 1. So you and again, so it's not written explicitly in the problem statement that you need to do maximum of these 4 operations. But again, if you read the problem statement, think about a little, think what options do I have? It's quite obvious that you have these 4 options. Well, I can put them in bracket. Okay, so yes, I remember you can do it like this, but okay. Check my submission. Wait, remind me please your handle. I don't remember. Who are you? Ah, LGM. Okay. Okay. So that's how you do it. Okay. Makes sense. Okay. Did someone manage? Okay, someone managed to fail this problem first. So let's find the mistake. Okay, so I find position of 1, position of n, and then calculate maximum of distance. So somewhere here should be a mistake. 1 minus maximum. Okay, that sounds strange. Why it's y minus 1 maximum? It's 0. So the leftmost position is 0. So it should be 0 minus maximum. Just mx or man. Okay, just small mistake. So it's not covered with examples. That's fine. That's fun. So in the examples, you always put to the right. You never put element to the left. Here you put it to the right. And here I have 7. Okay, so here I put 7 to the right. Yeah. So again, in these examples, you always put element to the last position. Never move it to the first position. Yeah. No, why not? So this is just a small mistake. You fix it, you move forward. Okay, some people didn't manage to solve first problem, solve third problem. That's strange. Not sure how you did it. I forgot to okay, okay, so you're allowed to participate as teams. Okay, because I forgot to turn it off. Okay. That's it. So that's problem 1. Okay. Let's go to problem 2. Problem 1 is not very interesting, so let's go to problem 2. Play back. Let's make it faster again. Boop. Uh, Problem B has long problem statement without any formulas. So you kind of need to read all this text and convert it to formal problem statement. No, it's okay. So this part of the competitive programming, to be able to read problem statements and understand what's going on. So what's going on in this problem, we have some fruits given to you as strings to make problem more challenging, and some prices, and you don't know which price assigned to which fruit, and you're interested in what minimum and maximum possible cost of these fruits. Okay, so I do it like this. I count how many strings I have of each type. So for every type of fruit, I count how many fruits of this type I have. Then just put these numbers to this array C. Now to maximize the price, or to minimize total price, I need to assign lowest price to the most frequent fruits. Yes. So I sort fruits by frequency in decreasing order, and sort prices in increasing order. See. So I and then I will just assign the smallest price to the most frequent fruits, and that's it basically. So it's nothing very funny. Okay, then I actually read the problem statement and figured out you not only need to minimize but also to maximize. But okay, so I just copy pasted this code once again. And if you want to maximize, you do the same but assign maximal cost to the most frequent fruit. So you just change the order of sorting and get the second number. Okay, let's just, it's hard, it's not fit. So let me copy the code from here. Boom. Boop, 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 boop. So again, here so here I'm reading the input, and I don't save it as array. So I just read the strings and immediately increase my counters. So I need only these counters, right? So now I transform this counter just to array of integers. So for every fruit, I count how many fruits of this type I don't need. Yeah, and then just sort and combine. Then again sort and combine. So I copy paste the code. Okay. If you want a clear code, you can move this to function, then just change order of sorting, something like this. I don't need clear code, so I'm okay to copy this code twice. Okay. Let's read how you do it. Actually, I believe. Let's read someone. Let's read Alex. With a lot of promise. What can go wrong? Actually, let's read your mistakes. Interesting. Always interesting what mistakes you may make in these problems. Okay, here I put that strange way to read the vector, but okay. You can just create vector of this size and read the elements directly to this vector, so you don't need to push them one by one. Counters, okay, okay, and here I put okay, that's the same thing. So you have this array now, sort reverse. Okay, you sort reverse, I instead sort in decreasing order. Calculate sum, sort again, just reverse. Calculate the sum. What do you have, integer overflows? Probably yes. No. Yes, you have integer overflows. Oh no, no. You just not initialize something. You not initialize some variable. Which one? K. And okay, K up to M. Looks like you didn't initialize something. But I don't see which one. So read N, read M, read array. Okay, strange way to read array, but okay, you do it. Map. Okay, C, pushback. Looks fine. Sort, reverse. Sum equals 0. Sum plus equal this. It looks okay. Do you see the problem? Hmm. I'm just curious about your mistakes because when you find some mistakes, you try to avoid them in future. It's always better to learn someone's mistakes so you don't repeat them. But how? It looks okay. So I read m, a n times read push. Looks okay. So it's a string in +1. Looks fine. C autoconst. This also looks fine. Am I blind or what? Where's the
Why is this some loop till m only? Shouldn't it be n?
it shouldn't be m. Yes, right. Yes, if you have less than m elements. Okay, right. Thank you. It will be like this, yes. Okay. No, it's good. Okay. You found the mistakes in someone's code. That's actually before in ancient times. So they do it now. So even now in code forces, you have ability to hack someone's code after the contest. But now I believe people don't do it that often. Before in top coder times, it was very popular. So you not only need to write your own code, but you need to be able to hack someone else's code. Yeah. Now it's not that now it's not that interesting, but back in the times it was very interesting, just nice challenge to find mistake in someone's code. Good. So let's move forward. Next problem, a shell game. Okay, shell game is a nice problem. Okay, so the problem is, so we have some we have 3 elements and we make some permutation of these elements n times, and the trick is that n is large, so we cannot apply just explicitly n times because n is too large. So problem is actually solvable for larger sizes of everything, but here the simplest approach is just to see that after 6 operations you have the same permutation. So I just checked here just to be sure. So you can calculate n modulo 6 and have the same operation. Same operations, because every 6 operation you move to initial state. What I'm doing here, so I believe the trickiest part of problems like this is that, so you mentioned, so in problem like this you have problems about some permutations. Here you have just permutation of 3 elements, but still, so you have some permutations. You need to carefully think where you have like direct permutation when you have the inverted permutation. And what I'm doing here, so just okay, it's too fast. Let's do my submissions. Get it here. So how I solve problems like this is like here. I think about it in the following way. I think like if I get 3 elements, I just attached some numbers to it. Yeah, so I have. So here I have 3 shells. Yes, some of them contain something ball or what? Something some ball, yes. So I have 3 shells, one of them contain ball, 2 of them contain nothing. Yeah, so I will just imagine that I have 3 balls. Yes, and I just write numbers to these balls. So I write numbers like 0, 1, and 2 to these balls. Yeah. And when I swap two shells, I just swap these balls. Yeah. So here I make permutation. So this permutation P. So Pi is just equal the number attached to the ball, which is now in position I. So initially I have balls 0, 1, 2. Now after every operation, I just swap these two balls. Again, I just tell you how do you think about permutations without getting mistake between normal permutation, invert permutation, where you apply operation to permutation. Here are very simple operations, but in some another problem it may be more interesting, like when you combine permutations, when you make one permutation, then on top of it make another permutation. It's always tricky to think about, okay, do I need to apply normal permutation or inverse permutation? And so it's what I'm doing here, I try to visualize it as some physical objects, you know. So here I have so every number of this permutation have some meaning. Yeah. So here number in permutation is just number of the ball which is currently in position I. Yeah. So every time I apply the operation, I swap two balls. Yeah. Okay, it's just a nice trick to solve problems contain some permutation operation. Okay, so in the end, I just need to output which ball is in the end in position X. Yeah. Just brute force all combinations. Oh, also possible. Yes, you have only 6 permutations. You can just brute force all 6 of them. Totally makes sense. Yes, you can totally do it. Let's actually read your solution source. Sorry, I'm interested. So what was the most popular approach? Brute forcing 6 permutations or doing cyclic? No, that's exactly what I'm doing. Oh no, I to see what? You generate these 6 permutations and then output this. No, okay. Why not? Actually, out of these 6 permutations, you need only one, so you don't need to generate all of them. But good. Read someone else. It's also my okay. So that's brute forcing all possible combinations. Okay, it's totally valid solution. So this solution works. That's the most important thing. The problem is why I don't usually like to write like this, because it's very easy to make mistake. So imagine you make mistake in one of these many numbers. It would take a lot of time just to find which number is incorrect. It's doable. No. Sometimes you have to do something like this. But if you can avoid something like this, I would usually try to avoid this. But again, no, this is small problem. So so not that many numbers. So you have like 12 numbers. Okay, you can check 12 numbers by hand. Well, problem D is very easy. Again, when I read it first, I didn't think it is that easy. So the problem statement looks kind of scary. It's because you have some cyclic shifts, lexicographically minimum. Sounds scary. Okay, so it turns out the problem is very easy. So what you're doing, you take some substring and decrease all the characters by 1, basically. Yeah. So you move from character to the previous character, and A is replaced by Z. Okay, so you want to minimize the resulting string. So to minimize the resulting string, you need to decrease characters. Yeah, you decrease all characters except A. So A is special character. Yeah. Let's find the leftmost character, which is not A. So we can decrease this character and make it correctly minimal. Yeah. After this, you decrease all characters until you find another A. Yeah. Yeah, the only tricky part is when all characters equal to A. If all characters equal to A, then you need to decrease at least one character. Yeah, so you decrease the last character, so you have A, Z. Pretty straightforward. So I'm not sure why it is in position D. Maybe it has some incorrect difficulty in code forces. Well, again, that happens. Yes, sometimes you have some easy problem in the middle of the contest. So again, we simulate some random contest. Sometimes you have situations like this. Okay. You need to be able. So if you see the problem, just solve it, even if it is in position in the right part of the contest. So even one of the last problem of the contest looks easy, just solve it like it is easy problem. Maybe it actually is easy.
I have a question.
Yes.
Is it always true that when we have to minimize or maximize something lexicographically, then it has to be greedily?
Yes, lexicographically minimal string just by definition. What does mean lexicographically minimal string? It means so you go from left to right and try to minimize each character. So you minimize first character. When first character is minimal, you try to minimize second one, then you minimize third one. So almost always when you have something about lexicographically minimal strings, you have something greedy approach. So you just go from left to right and greedily try to optimize each character. Then after that, it depends what you're doing next. Yes, but this part is always the same. So you go left to right and try to minimize each character from left to right. Yes. Problem E. Okay, problem E is okay. Also looked kind of scary, but turns out very easy problem. So you have this cyclic sequence from 0 to 15 and back to 0. And you're given some some array up to 92 numbers, which is part of this cyclic sequence. And you need just to find which part of the cyclic sequence you're in. Very straightforward. So because everything is small, so it's 92, 30. So I just check all the possible positions and find which one fits. Okay, not sure why this problem is in position E, but again, that's the contest. Here I just check. So m equal 30. I just put it in constant, so I don't have number 30 multiple times in my program. Yeah. So I first fill it somehow, and then try all the starting positions, and then simply check brute force if it fits. You can use something more clever, but you don't need to. You don't need to.
So I assume that the days are always correct, and I've got an O of one solution. Just it's 5 if conditions.
Okay, just contest like this. So that's it. Nothing actually to discuss here. So that's the whole program. So you again, many ways to solve it. You can just look at the first two characters and understand what's going on. So here I just simplify because I can, but okay, not very fun problem actually. But then go to problem F is fine. Problem F is fun. So let's talk about problem F. Okay, here let's talk about it first. So what we have in problem F, we have YouTube. No, problem F. So let's decode what's happening here. So I have some parts of the game, again parts of the game, and I have some dependencies between them. Yeah, so some parts can only be solved played after I played some previous parts. Yeah. Okay, so let's decode it in normal language. I have a direct graph. Yeah, and what I'm looking, I play in some part of this game. Complete. So I complete parts of this game in topological order. Okay, so if you never saw topological sorting and DFS, it's time to learn topological order in DFS. Okay, so basically what's happening? Let's discuss this example, for example. So here I have 5 parts, 1, 2, 3, 4, 5, and they have dependency between them. So part 1 depends on part 5. Yes, you see. Part 2 depends on parts 5 and 2. 2 depends on 5 and 1. Part 3 depends on 5 and 4. Oop, 5 and 4. And part 5, no, part 4 depends on 5, like this. So you have a graph, and you need to complete these parts in topological order. So for example, you can complete 5, then you can complete 1, then you can complete 2, then 4, then 3. Or you can start with 5, then do 4, then do 1, then do 3, and then do 2, and so on. So you do it in some topological order. So all these edges go from left to right. Yeah. Poop, poop, and so on. Now, how do you measure time? So you measure time. So each part you can complete only in one specific location. So you have 3 locations, 1, 2, and 3. And for each part, you know the location of this part. So they have 2, 2, 1, 1, 3. 2, 2, 1, 1, and 3. Yeah. So you need to find topological order such that if you do it, and you can move between these locations. Yeah. And you want to minimize total time you spend like moving between these locations. Okay, like in this case, so what is the best part? 7 hours, 5, 3. Okay, so let's say the optimal find is 5, then you do 4 and 3. So you have, you're saying location 5 and location 3. Then you move to location 1, complete 4 and 3. Then you move to location 2 and complete 1 and 2. Yeah. So you spend 1 hour to complete every part, and then you spend 2 hours to move. 1 hour to move here, 1 hour to move here. That's already some complicated problem statement, but it gets even so. So now we need to look how we move between locations. And if you read this part, you will see that the way you actually move, you move like in clockwise direction on this picture. So you move from 1 to 2, from 2 to 3, from 3 to 1 in 1 hour. So you spend 1 hour to move along this cycle. So you actually don't have much choice where to move. Yeah. And that's important. If you had choice where to move, it's actually a much harder problem. Yeah. But here you basically move along this cycle and complete what you can complete. So again, how do you find topological order? So if you never did it before, so how do you find topological order? So one of the way to build topological orders like this, you just go from start from nothing. And then every time you pick some node which has no ingoing edges. Yeah. So you build topological order. So the first node topological order is the node which has no ingoing edges. It's node 5. So node 5 has no ingoing edges. Oop, oop, oop. So I can take node 5 and put it in the first position. Then you remove node 5 from your graph, remove all these edges, and find another node which has no ingoing edges. Now I have two options, 1 and 4. Basically, it's greedy algorithm. Yeah, so I complete all the parts which I can complete. Yeah, no, it kind of makes sense. So if you can complete some part now, you have no reason not to do it right now, right? Yeah. So even if you don't know about topological sorting and stuff like this, you can find the solution just by thinking greedily. So again, if I am standing somewhere and there is a part which I can complete right now, yeah, it's always better to complete it right now. Yeah, there is no advantage skipping it and complete it later. Yeah. So So you see that you move along this cycle, and you can greedily complete all the parts that you can complete. So that's what we will do. I just noticed it's 200. Okay, I solved the problem for higher constraints again. Okay, so what we'll do, I will move along this cycle and just greedily complete all the parts which I can complete. And I do it in the same way like you build topological ordering. I will remember for each part how many dependencies does it have. And when it has 0 dependencies, I will mark it as this task is ready, not task, this part is ready to be completed. And then I will just greedily move along this cycle and complete everything I can complete. And when I complete everything, I stop. That's the plan, okay? So again, I will move along this cycle and complete greedily all the parts which I can complete. That's the plan. Now let's see how to implement it. So so here I just read these positions. Yeah, another trick is you can choose the initial position here, but there are only 3 options, so I will just iterate over all of them. Let's go. So here I read. So here I do it like I normally do with graphs. So I create this vector of all the edges. I need outgoing edges. So for every part, I make list of all the parts dependable on me. Yeah. Calculate degrees. Again, this part is trivial if you know how to do topological ordering. So basically, I do the same thing like I do in topological ordering. Here I choose what will be the starting node and just greedily go and do. Let's keep this. It's too long. Here, so this part here is basically a copy of the normal algorithm for building topological ordering. So I have these queues, not queues, they are stacks, but it doesn't matter. Yeah, so I have these queues of the parts ready to be completed, and I have 3 queues for each location. So I have for each location, I have the queue of the tasks which are ready to be completed in this location. And here I just go, so I have my current position, I just move. Okay, I decided to rename everything. Okay, so here I take some task, I complete it, then iterator all tasks depending on it, decrease number of dependencies, so R is number of dependencies. And if number of dependencies is 0, then this task is also ready to complete. And I will put it into the queue. So it's pretty standard algorithm for making topological sorting, but also you need to move along this cycle of 3 elements. So that's it. Any questions? Again, I believe this is a fun problem. Not very hard problem as for problem F, but at least it is fun. So yeah. Let's read someone. Let's read you for fun. Okay. Okay, so that's again that's the same number of edges. We read all. Oh no. No. It's not edges. It's we put every task to the bucket. So we make bucket for each location, and we move tasks for specific location. Okay. Here I make edges, but make them backwards. Okay. Here I think you choose the initial location. So L is my location, size is N, whatever it means, map. Okay. So while I size, I mean, I think it's while there is something left, increase time, I think. Yes, this is time. Then while one, okay, why not? Pa-pum. Okay, so you have, okay, so you solve problem for small constraints like here. So you just look at all problems at or all tasks in this location, check if it's mpj, not sure what's happening. It's 0 or 1, why? You can make array, okay, not sure why do it. If it's only 0 or 1, you just can make array. See, if it's already done, you continue. If not, you look at all the dependencies and see if all the dependencies are already completed. If yes, then I can do this task. Yes, I do this task, k equals 1. Okay, k means I did something. Okay. Nice. So again, so this is correct implementation of the same algorithm, just not that fast as mine, but yes, it's perfectly fine. So if constraints are small, that also works. Nice. So if you didn't see this algorithm before, just invented it during the contest, good for you. Really nice. Hard to implement? Probably. I would say not as hard to implement. So it's again, this is okay. Let me see. So what? How many lines do we have here? Like 60 lines of code. No, not the hardest problem we had. Okay, so again, if you didn't know this algorithm before, then you need to invent all these lines for the first time. Good for you. So if you did it, solve it, perfect. But if you know this algorithm of building topological ordering, then like half of these lines are just standard lines. So you don't need to invent them. You just invent this part when you move from location to location. And instead of single queue, you have 3 queues. So for every location you have queue. That's the change. Yes, but this problem is tricky. Yes, I agree. So some skips. Let's it's you again. Okay. So what's your problem again? Repeated for every node. Hmm? What? Hmm. So what you do again? Something done. Okay, if everything done, then break. Then you look at all tasks. See if position is not this, then continue. Okay. If already done, continue. Okay. Good. Look at all points. If not done, end position is not core. Why you have this? Why PC is not core? You submitted it later. Okay. Okay, so you fixed it. Got it. Is it the same? This looks different. Mm.
So basically, the issue was that if our parent is on the current location as our location,
Mhm,
and if for some reason it appears late in the order, so I go up and take all the PCs which are take all the games which are on the current location,
mhm,
and if on the topmost node there is no parent, then all of them can be done. And if there is some topmost node which has some incomplete parent, so we can skip it.
mhm. Okay, okay, okay. Okay. We have just two problems left very fast today. Okay, we'll finish earlier today. Problem G. Problem G is fun. Again, some constructive problem. We had a few constructive problems last week, and here's another one. Now you need to fill the rectangle with small rectangles of size 1 by 2, 2 by 1, and 2 by 2. That's it. So you have some number of planks of this three dimension, and you need to fill the given rectangles using only these planks. Okay, so here, okay, the trickiest part for me was to understand which one is which, because they don't have picture. They have only examples. So just to show you. So they don't have any picture. They have only examples. And like in this example, you have a equals b in all examples. Okay. So code forces is slow today. So a equals b in all examples. So I just didn't understand what is 1 by 2, what is 2 by 1. But then I noticed that here you have room n by m. So this first element must be the same as this n. So it's just first element is number of rows, second element is number of columns. Yep. So 1 by 2 means I have one row and two columns. Yeah. Okay, so that part was hard for me to understand. Okay, so here I just drew this picture for myself so I don't forget which one is which. No, here the idea is very simple. So, like if you have, no, you can't do anything tricky with these dominoes. Like these dominoes are very simple objects, so you cannot do. So when you don't need, when you just need to fill somehow the rectangle, you basically cannot do any tricky things. So so you can, but you don't have, you don't need to. So you can just glue. So if you have some odd dimension, then in this one extra row you need some dominoes of specific type. Yeah. No, again, so like if n is odd, then here you need some row of horizontal dominoes. Yeah. But everything else can be split into squares 2 by 2, and that's kind of that's it. So you can't so you can glue together all these dominoes. You can glue together all these dominoes, and the only thing that's left, you may have at most one domino of this type, one domino of this type, and then you cannot do anything. So if you have one horizontal domino and one vertical domino, it means there is no way you can put them somewhere. So that's it. So I will make one special row of these dominoes, and just fill everything else as squares 2 by 2. Now the tricky part is the implementation part. So you need to implement all these things. So you need to draw the picture, yeah. And in this picture, you need to encode all the planks using letters. So the touching planks have different letters. Many ways to do it actually. So yes, if both dimensions are odd, it's obviously impossible. Okay. Now I will just put the result here. Yeah. So yeah. So here, if n is odd, then I need to make a row of horizontal planks. If I don't have enough planks, I say impossible. If I do have enough planks, then I make this row like this, for example. Yeah. I'll just do it like this. Yeah. So I will alternate between A's and B's. So we have AA, BB, AA, BB. Yeah, and here I just check. So you see, that's something I normally do when I have implementation tasks. So I implemented first part of the solution, just fill this row. I will check that I don't have any problems at this point. Yeah. So okay, these samples are the trash. So I need to find my own samples because all the samples are even. This is impossible. Very boring samples. Okay, that's actually that's good. So in few previous problems, authors give us very nice examples so you can find all the mistakes. Here they actually force you to make your own samples, and that's good. It's very important skill to find good good tests for your solution. So here I need to test my own solution. So I need to make some odd dimensions. Yeah. So I make this odd dimension. See that I alternate A and B. Looks okay. Oh, you see AA, BB, AA, BB. Looks very promising. Now I just need to do the same for another dimension. So I will just copy paste this code because I can. Then I need to change all N to M, all I to J. Just basically check. Okay, you may see that I already made some mistakes when I do this. But that's okay. I will just read the code once again and try to find all the mistakes. Yep. That's basically was the last of it. Yeah. Yep. So look. So I check that I have, and I check in the next direction. Yeah. So in both directions, I successfully filled this last row and last column. Now I just need to solve problem even by even. Yeah. And you do it by split everything in squares 2 by 2. So I check. So how many squares do I need? I need n by m divided by 4 squares, and I can fill C plus half B plus half B plus half A plus half B. Yeah. So this is total number of squares I can fill, and this total number of squares I need to fill. So if I don't have enough, it's impossible. I just copy paste impossible multiple times. So it's not very good style, but yeah. So I have I believe that's the fourth time I have something impossible. And here I just fill the squares one by one. Okay, to fill the squares, so I need to be sure that touching tiles have different letters. So I use letters A and B here. So here I will just use letters C and D. Yeah. So I will color them like in chessboard. Yeah. So I will use letters C and B in chessboard fashion. Yeah. That's it. Okay. Decide to rename it to X. And to even this what again forbid if is the same as reduction and to even. So what we did, so we did reduction to even. So we for both dimensions, if we have some dimensions is odd, we remove one line, one column, or one row. Now both dimensions are even. Yes, I make m minus 1. And now I just fill these squares, and I fill them in chessboard fashion. So I use letters C and D to make like chessboard coloring of these squares. Oh, let's see. So I have, you see, I have A, B in the bottom, and here I have chessboard coloring. Yeah. Okay, so now I just need to color. So when I have, okay, now I have some dots left because I don't have enough tiles 2 by 2. I only know how to place tiles 2 by 2 by now. Now to fill all these, I need to use vertical or horizontal tiles. And I will do it, we will do it. Just write some more code. Okay, so if I have 2 horizontal tiles, so copy paste, I love copy pasting code. Okay, so we have this equals to C, and I need some another letter. So I use letters C and D alternating. Yeah, so I need some another letter not equal to C and D, but also alternating. So I decide to do C plus 2. Okay, it should be X. It should be X and X plus 2. Yeah. So I will use letters C and D alternating here and letters E and F alternating there. Okay, that's you can do it multiple ways. Okay, you have 26 letters. That's more than enough. There are tons of ways how you can assign these letters so neighboring touching tiles have different letters. Yes. You can just, for example, okay, you can attach the character based on the coordinates of this tile, like x plus y modulo 26. Yeah. Then you make sure nothing that touches should. Okay, because I have c instead of x, and now you need to put into place because I copy pasted the code. See, I know I have some dots because I have mistakes because I didn't fill some. Okay, that's something I do in a lot. So because I feel the answer with some dots or question marks sometimes, and then it's easy to see which places you missed. Okay. I see. So here horizontal parts are fine. Vertical are not good. So here I put vertical tiles. Here I mistake again. Okay, I read this code. Okay. Yeah, now it's finally complete. You see, I put the horizontal tiles, I pulled vertical tiles, and put everything in. No, it took some time to implement all the details, but overall, that's it. Was it easier than F? Probably yes, probably yes. Let's look some solutions. No, someone spent a lot of time, +9. How do you solve it wrong? It's actually incorrect field, whatever it means. 56 by 59 with this constraint. No idea. Something is incorrect. Okay, I will not find mistake in this code. So we don't have enough time to find mistakes in this code. But again, that's because you have a lot of code, you see. So that's when you copy paste a lot of times, you need to be ready to find a lot of mistakes. What is the final code? No, it's still the same. So okay, so we can look at the difference. Okay, so we just rewrote this part. Oh no, it's almost the same. It's just diff is okay. Okay, this diff works strange. Okay, so you change the part which assigns the characters. Okay, this is tricky part. So again, this part is kind of tricky. So just to assign the characters in such a way that touching tiles have different characters. Barely made pencils. Let's read your code. Oh, +10. Nice. You had some quality time with this problem. Okay, that might make sense. Okay, it's a lot of code. I'm not sure I can read it. It's too complicated. Okay. Okay, so you see it's not that easy problem. So if you solve it fast, good for you. But it's not easy problem. So many people spend a lot of time and made a lot of mistakes in the problem. It's a nice skill to implement problems like this from the first try and submit it and get accepted. It's very important skill because when we will see some other problems, you have both like mathematical core of the problem. So you need to actually find some idea and maybe implement some algorithm. And then on top of this, you have some implementation details. So if you stuck at the implementation details, you will not get to this interesting part. Yeah. So just spend more time solving problems like this. After few, I would say years, but maybe faster. So you will see that it is easier and easier every time. So after you solve problems, and you may revisit your old solutions as well. So when you solve the problems like this, you may after a week, after a month, after a year, come back and try to revisit your solution and think what you can do better. So maybe my solution is too complicated. You can do all the same things in much easier way. Yeah. Just yeah. Let's go to the final problem. Okay, so final boss of this contest is problem divisibility. So okay, so let me show you. So I will just write the code here, but it's okay, I can show you. So what we do in this problem? Again, this constructive problem plus mathematics plus something, many things going on in this problem. What we need? We need to find some set of numbers which has exactly k pairs when number is divisible to another number. Graphs, in some sense, you may think about it as graphs. I would think about it as just okay. Let's think about the graphs. So what I'm doing. So if you have let's say numbers like 1, 2, 3, 4, 5, 6. You see which numbers divides which. So I have like one divides everything, then 2 divides 4 and 6, then 3 divides 6. That's it. Yeah. So you have this graph. You can remove some nodes from this graph. So the resulting graph has exactly k edges. You may think about it like this, but hard to explain what's happened next. So if you play a little bit with this model and think what's going on, and just think, okay, if I just start from the full graph and try to remove some elements from it. So I remove some nodes until I have exactly k edges. Yeah. Will it be always possible? Well, it looks like it's always possible because you have these primes. So there are, okay, just because how this graph is constructed, there are numbers like this, like 5, which have only one edge. So there are primes. Well, specifically, you need primes greater than n over 2. Yeah. So if you have, so these are your numbers. So if in this part you have some prime number, so nothing divides by this number, and this number is divisible only by 1. So this number forms only one pair. And okay, if number n is large, you have a lot of prime numbers here. Okay, I don't know the proof for this, but okay, number of primes is kind of like n divided by log, plus minus. So there should be a lot of numbers like this. And yeah, and my number, okay, so if I just remove numbers from right until I have, so I remove number here, yeah, number of elements here is kind of, so number of divisors is very small. So again, what was my plan? I'm going right to left and just greedily remove elements if I can remove. So if I can remove some element, I will remove it. That was my initial plan. It turns out it doesn't work on example. Thank you for the good example, by the way. But so my initial plan was to go from right to left and just remove the element if I can remove it. And I thought it will work because I have a lot of primes here. Yeah, I have a lot of primes, and actually number of divisors is small. That was my intuition. Yeah, number of divisors is small, so I can probably I can easily find the elements I can remove. It's actually hard to explain why number of divisors is small. Number of divisors is just small. How small? It's a good question. For numbers up to 10 power 5, I believe it's like 1,000, something like this. Maybe less than 1,000, maybe just 100 divisors. So all number of divisors is really small. So if I go from left to right, try to erase numbers which I can erase, then probably I will always be able to get number exactly k. Yeah, that was my intuition. What I'm doing here. Now, how do I implement it? So I just so what I'm doing here, I build the array of divisors. So here I build the array of divisors. So that's the whole code. Yeah. So for every element, for every number, I have array of all the divisors. Very simple code. Yeah. And then I will go from right to left and try to remove elements. So if I can remove element, I will remove it. If not, then I'll fix this element and fix all its divisors. So I go, if it's fixed, so it's okay, spend a lot of time here. So here, so if it's fixed, I continue. If I can remove it, so if I cannot remove it, so if I remove it and I have a number less than k, I fix this number and fix all the divisors. If not, then I remove this number. Okay, this shouldn't be here, but okay. I remove this number and decrease my sum by this. You should put else here and so on. So yeah, a lot of mistakes in this code by now. Yeah. So basically this is my plan. So if I cannot remove number, I leave it. If I can remove it, I remove it. What? Okay, we just discussed. Okay. At this moment, that was okay. That was bad. So I implement all this and thought it's all going fine. Then I found this second example, 6, and the answer is here, but I found no. And I need to draw this. So I drew this example and think what's going on here. And it turns out it's actually this greedy algorithm doesn't work, because here you have 8 connections. If you remove 6, oh no, you have 1, 2, 3, 4, 5, 6. 1 second. Why it's 8? I need 6. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, I have 8 connections, so I need to remove 2. But if I greasily remove 5, yeah, I need to remove 1 more connection, but 3 is already fixed. I can't remove 3. So removing every element will destroy 2 connections. So I need to leave this 5 and remove this 3 instead. That was actually a very, very sad moment. So when you learn that your greedy algorithm doesn't work, but again, the idea was fine. Yeah. So the idea was that there are a lot of prime numbers that I can remove. So I thought, okay, it just doesn't work on just some small. So when n is small, you may have some corner cases, but when n is large, that should be always enough prime numbers. So I just decided, okay, I will just write a brute force algorithm. I read your solutions, and it looks like it's actually the only case. Yes. The only case when you have problem is when you have n equals 6. Yeah. No, I read someone's code. I don't remember. So they have only special case when n equals 6. Not this. Okay, cool. Okay, we'll read them later. So it looks like this is the only special case actually in this problem. So this 6 is tricky to get, but I didn't know this. So I just implement brute backtrace algorithm. So So I will just use brute force to find the key combination using backtracking algorithm. Need to, okay, I need to rewrite this part a little bit. Now, implementing backtracking algorithm. So backtracking will work like this. It will kind of, it's kind of the same greedy, but with backtracking. Yeah. So I will try to do the same greedy thing, but if I fail, I will try an alternative approach. Yeah. So again, what I'm doing, if I can remove number, I will remove it. If it fails, then I will stay. I will leave it. That's the plan. So, okay, it's boring. So, and I count how many times I fix number. So number. So if I keep the number, I keep all its divisors. It's actually not a great. Okay. It's actually not correct backtracking. So it doesn't check all possible configurations. Okay, so I cannot leave this number and remove divisor. Yes. Okay, so it's not perfect backtracking. It doesn't backtrack over all possible combinations, but it works. So I okay, let me write. Let me just read the whole code. Too slow. Here. So this is basically backtracking. So I'm going for position n. My current sum is s, and I want to achieve some k. Yeah. I look at this number. If I reach the beginning, I return this if true if I have correct sum. Now, if I cannot remove this number, then I go to the n minus 1. I keep no. If I can remove this number, so if it is not fixed and removing makes number greater or equal k, so it's safe to remove this number. I remove it. My sum is this. Yes, I go to n minus 1. If it succeeded, I return true. So I try to remove this number always first, if it's possible. If it's impossible to remove, or if I fail to remove, then I go here. I try to keep this number. I keep this number, so I fix all its divisors, and recursively go to n minus 1. Okay. Not the best backtracking algorithm I implemented. Okay. It was enough for this problem. I read the tutorial of this problem, and they say that actually there are a lot of correct approaches of this problem. So you can do almost anything and still succeed because there are a lot of solutions. So if solution exists, then there are a lot of solutions. So you need to deal with small cases somehow. But for large cases, it's very easy to find some solution with answer k. So just many approaches just work on this problem. Let's read someone else. Oh, it's very short one. It's impossible to read, but it's really short. Let me do it like this actually. I just cannot read it. Okay, that's the same. We count number of divisors. So you don't make list of divisors. You just count how many divisors you have. Yeah. Then we go calculate prefix sums. Why not? Now, if k is greater than total sum, answer is no. Makes sense. Actually, answer is that, so they tell the k is up to k is up to billion. But if you look at total number of divisors for all numbers of it's actually pretty small. So it's just a few millions actually. So this billion will never be achieved. Now let's read this part. So we have this sum included. Okay, so we remove some elements from the right until we have something greater equal k. So we find the longest prefix, which gives us at least k edges. Okay. Here I have no idea what's happening. So I make array of pairs, number of divisors I, sort from I plus 1. Not sure why I plus 1. Because you, okay, maybe you iterate from 1. Okay, so I take number with small number of divisors first. Reverse. With large number of divisors first. It looks like the same. No? Ah, not the same. So you don't go, okay. So you just do greedy algorithm, but in different order. So you sort elements by number of divisors, and in this order apply this operation greedily. Okay, and this also works. Interesting. Okay. What's time complexity of backtracking in my I have no idea. Again, because I think it's almost always linear, because it's almost always you go here and immediately get through. So I believe you never make two recursive calls, only in the very end. And if you're backtracking, use only one branch. So again, it's if you have two branches of backtracking, but only use one, yes, it's not backtracking. It's basically you go deep, 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 deep. In the end, maybe you have small branching. So I believe just because of the special graph in this problem, this backtracking works in linear time. Yeah, because you actually only have backtracking in the last elements. Or maybe not at all. Maybe you only need this backtracking. Yes, you probably only need this backtracking for small values of n. So for big values of n, it's just linear. So it's just greasily. So you just do this greasily and always succeed in the end. Okay, so that's it. Thank you for watching. See you next week.